Okay, so 31, we're simplifying some expressions here. This is 7 square roots of 5 squared. There's lots of ways you can think about this. I'm going to spend a little time on this page here just because there might be some review needed. You can write it like this, and then we have essentially 4 numbers multiplied together. 7 times square root of 5 times 7 times square root of 5. So 7 times 7 will be 49. Square root of, that's these two. Square root of 5 times square root of 5 will be 5. And then 49 times 5 will get you 295. Some people also like to think of this kind of problem as the squared distributes to each one. So when you square these, you get 7 squared and 5 squared. So you'd get, or sorry, square root of 5 squared. So you do get like this here, 7 squared times root 5 squared equals 49 times 5. And you get to the same spot of 295. And evidently I'm not so good at math in my head here. So actually 49 times 5 is 245. Same here, 245. So sorry about that. That's the correct answer. But the process is correct here. On B, common problem of having a radical in the denominator. So whenever you have a radical in the denominator, the way you clear it out is multiply by what I like to call is the funny form of 1. So it's going to be a fraction that's going to equal 1, where the numerator and denominator of the fraction are the same, and they equal that radical that we want to get rid of in the denominator. So that's why I've chosen square root of 2 over square root of 2. And then we must multiply across since these are multiplied here. So we have 8 times root 6 times root 2, and in the bottom we have 2, because root 2 times root 2 equals 2. And then this simplifies to 8 root 12. So when you have radicals and you multiply them, the two numbers multiply and stay underneath the radical. Divided by 2, and then we get 4 square root of 12. And now there's actually a perfect square factor in the 12 here. So we can think of this as 4 times the square root of 4 times 3. That 2 is a perfect square, or that 4 is 2 squared. So in order to take it out there, we have to take 2 comes outside times root 3, and then the final answer is 8 root 3. That's one approach on this. A second, probably more quicker approach is you could think of this when you have, just like you can multiply, when you have two numbers under radicals that are multiplied, you can take the radical of the product. Same thing here with the quotient. You can really rewrite this as 8 times, and then we can put the 6 and the 2 underneath the radical. 6 divided by 2 is 3, and you get 8 root 3. Much faster way to get at it, but either way will work. C here, pretty straightforward application. The trick is to make sure you do the order of operations right. So 3 squared is 9, plus 4 squared is 16. Square root of 25 equals 5. Here's something to make sure you don't do, which I see more often than I would like, is if you have square root of 3 squared plus square root of plus 4 squared, this is not equal to the square root of 3 squared plus the square root of 4 squared. You cannot distribute the radical like this. You can't take the radical or the square root of each piece and add them. So this is a common error. And if you kept doing this, you'd get 3 plus 4 equals 7. So make sure that you don't do that. This one here is an exercise in making sure you collect like terms. So square roots of numbers are just numbers themselves. And so when we see this here, we have 7 square roots of 2 plus root 3 plus 6 square roots of 3 plus root 2. So we can see here we have a root 2 and a root 2. We have 7 of them in this term, 5 in this term, so that gives us 12 of them. So we have 12 root 2s. And then here we have a single root 3 plus 6 root 3s. We can add them together to get 7 root 3. So it's kind of like adding like terms with variables, but instead of variables we're using these radicals here. And that is the answer for D. 32 is a straightforward application of the Pythagorean theorem, which I like to think of as leg 1 squared plus leg 2 squared equals hypotenuse squared, which I think makes it more clear than something like a squared plus b squared plus c squared. But anyway, we have two legs here, so it's just 7 squared plus 8 squared is going to equal the hypotenuse squared. That's what we're trying to find. 7 squared is 49, 8 squared is 64. We add these together, 49 plus 164 is 113. And then we take the square root of both sides to get h, so h equals square root of 113. So that answer is C. Another one where you're trying to find the hypotenuse. I think you learned some of the Pythagorean triples, which are some of the convenient patterns of numbers that create right triangles. One of them being 3, 4, 5, probably the most famous one. But there's another one, 8, 15, 17, which means that you could directly see that this is 17, but you don't need to remember or memorize those triples. It just makes problems faster. So you could always do this the good old-fashioned way of Pythagorean theorem. X squared equals 8 squared plus 15 squared. So you add these up to get x squared equals 289. Take the square root of both sides. X equals, in this case, technically it's plus or minus 17, but distances can't be negative, so you throw away that solution to get x equals 17. Well, here's another one. This time we're trying to find a leg. This happens to also be one of those Pythagorean triples. We saw that there was 3, 4, 5. And there's 5, 12, 13. There's 8, 15, 17. And there's another one, 7, 24, 25, which you could see that these two numbers are in the pattern. So a fast way would be to see x equals 24. But again, I don't really encourage you to memorize these triples unless they just come naturally to you. This is probably easier just to use the Pythagorean theorem, leg 1 squared plus leg 2. So leg 1 squared is x squared, leg 2 squared will be 7 squared. That equals the hypotenuse squared, and then you just go ahead and solve this. 7 squared is 49, 25 squared is 625. X squared will be 625 minus 49, which equals 576. X squared equals 576. Take the square root of both sides. X equals plus or minus square root of 576, which equals plus or minus 24. And again, we throw out that negative solution to get x equals 24 because negative distances don't make sense in this context. Well, look, we could identify this as a 5, 12, 13 right triangle. So we see a 5 here, a 13 here. So x would be 12, recognizing the triple. Otherwise, you can do Pythagorean theorem. 5 squared plus x squared equals 13 squared. 25 plus x squared equals 169. X squared equals 169 minus 25, which equals 144. X squared equals 144. Root both sides. X equals plus or minus root 144, which equals plus or minus 12. Throw away the negative solution to get x equals 12. The fast way to see this one is if multiples of Pythagorean triples are also right triangles. So if we know that 3, 4, 5 is a right triangle, we could take all those numbers and multiply them by 2 to get 6, 8, 10. Or you multiply them by 3, you would get 9, 12, 15. So these are all also right triangles. And so this one could recognize as a multiple of a 3, 4, 5, where 10 is the hypotenuse, 8 is one of the legs. So you could directly go to 6 by recognizing it as a triple. But if not, this is just like the last problem. X squared plus 8 squared equals 10 squared. X squared equals 10 squared minus 8 squared equals 100. Minus 64, which is 36. X squared equals 36. Take the square root of both sides. X equals plus or minus root 36, which is a perfect square, which is plus or minus 6. Throw away the negative solution to get x equals 6. This is one where it happens not to be a triple. You could try a couple ones, but you would see that you wouldn't find the pattern. So this is another standard application, Pythagorean theorem. Leg squared 1, which is leg 1 squared, I'm sorry, x squared, plus leg 2 squared, which is 8, equals hypotenuse squared, which is 12. X squared plus 64 equals 144. X squared equals 144 minus 64, which equals 80. X squared equals 80. So x equals the square root of 80. Again, I'm just going to throw out the negative solution, not even bother writing that. And so that is the right answer, but it's not considered in simplified radical form, but this wouldn't be wrong. Square root of 80 is a number, and it is the right number. But if we were going to simplify it to its simplest radical form, we'd want to try and find some perfect square factors in there. So let's just factor 80 here. 80 is 2 times 40. 40 factors into 2 times 20. 20 factors into 2 times 10. And 10 factors into 2 times 5. So it looks like we have 4 squared. So 4 squared times 5, or 2 to the 4th, but you can do it either way. So stick with it this way, but so then we can take that 4 out of in front, and remove the squared because it's coming out from under the radical to get 4 root 5. So the fully simplified answer is 4 root 5. But again, 80 is not wrong, just like the number 1/2 also equals 3/6. If I told you this number, if I said give me 3/6 of your pizza, you'd know what I meant. So those two numbers, these two numbers are the same, kind of in those two numbers, in the same way that those two numbers are the same. More Pythagorean theorem practice here. 4 squared plus 6 squared equals x squared. Here we're trying to find the hypotenuse, and now this actually wants it in simplest form. So this is probably more of an exercise in simplifying the radical. Equals 16 plus 36. X squared is going to equal 52. X will equal the square root of 52. Again, I'm throwing away the negative solution. And let's check out 52 and see if there's some perfect square factors. That's 2 times 26. 26 is 2 times 13. So 52 is 2 squared times 13. So that looks like a perfect square factor. So 2 squared times 13 is going to equal 2 root 13. And that's the answer. So here is more of an application problem of using Pythagorean theorem. So we know that ABDC is a rhombus. We have to remember what that means. That we have 4 congruent sides, and some of the property of a rhombus is that those diagonals are perpendicular to one another, and in fact they bisect each other. So we know that that's true. So I'm going to call this center point, we'll call it F here. And so we know AC is an entire diagonal this way, so this diagonal is 14, so we know that this piece is 7 and this piece is 7. This diagonal is given as 48, so this piece is 24 and this piece is 24. And so now if we zero in on one of these right triangles, I'm trying to draw this one here, let me erase that. This is the one I'm drawing here is the top right triangle, so A, B, and what I've called the center point F. We know that that piece is 7, that one is 24, so these are each half of the diagonal. Here's the rest of the rhombus here if I was going to sketch it in. And you could recognize this as a 7, 24, 25 triple, so that side would be 25, or if not, you can AB squared, which is the hypotenuse of that right triangle, is going to be 7 squared plus 24 squared. Which equals 49 plus 576. 625. AB squared equals 625. So AB is going to be root 625, which is 25. This problem's a little bit more algebraic. Probably easy to set up the geometry, but you have to do a little bit more algebra to get the answer here. So we're trying to find the length of the hypotenuse, but we need to find x. Again, the relationship for Pythagorean theorem is that leg 1 squared, which is x, plus leg 2 squared, x plus 7 squared. Make sure to put that in parentheses. It's going to equal x plus 8 squared. And now we just have to attack this with some algebra. So we're going to have to simplify. We're going to expand each one of these. So x plus 7 squared is x squared plus 14x plus 49. So the way to do that is you take the first term squared, that's over here, x squared, the last term squared, which is 49, plus the product of the terms times 2. So 7x times 2 is where I got 14. And so this one is a similar pattern. Get x squared plus 16x, which is 8 times x times 2, plus 64. And now we just need to, this is going to be a quadratic equation here, so we need to collect terms here. So let's do the x squareds first. We have an x squared here, an x squared here, but an x squared on the other side. So if I subtract, well here, let me, just in case someone needs the full algebra here, I'm going to just collect those together first. X squared plus x squared is 2x squared. We have a 14x, and then a 49 equals x squared plus 16x plus 64. Now our goal is we want to get this into something equals 0. So what we're going to do is I'm going to subtract x squared from both sides. I'm going to subtract 16x from both sides, and I'm going to subtract 64 from both sides. The reason I'm doing that is so that the right side here, these are all cancel out to give me 0. And then what happens here? I get x squared, 14x minus 16x is minus 2x, 49 minus 64 is minus 15. Now we have to solve this as solving a quadratic equation. So you could always use the quadratic formula, which I won't do here because this is actually factorable. So we want to find two numbers that multiply to 15 but add to negative 2, multiply to negative 15 but add to negative 2. So we think about the factors of 15. See, 1 times 15, that difference won't work. 3 times 5, well, it looks like we're in business there with 3 times 5. So we know it's going to be a 3 and a 5, but they have to multiply to negative 15, so one will be negative, one will be positive. And since we want them to add the negative 2, we know that this one has to be negative, because negative 5 plus 3 will be that negative 2, and that gives us x here. And then we solve for x. Each one of these factors, one of them, two numbers that multiply to 0, one of them has to be 0. So x plus 3 equals 0, or x minus 5 equals 0. This means x equals negative 3, or x equals 5. And then we have to check these solutions. So x equals negative 3 won't work here, even though these two triangles, these two sides of the triangle would work. We can't have a negative side here, so we're going to just throw that solution out. X equals 5 looks like it will work, and the triangle would be x on this side, 5 plus 7 is 12, 5 plus 8 is 13. Hey, does that look like a familiar pattern? But the length of the hypotenuse then is 13, which is the answer it's looking for.